Ricardo Figueroa is currently an associate professor and chair for the Motion Picture Science program at Rochester Institute of Technology, or RIT. Ricardo joined RIT after working at Kodak for 10 years. He'll close our session with Bayesian methods for radiometric calibration and motion picture encoding workflows.
Well, good afternoon, everybody. Thanks for being here. I'm guessing that none of you won the Mega Millions last night because you're all here, right? 1.6 billion. I wouldn't be here, but. Okay, so let's actually go into my paper for this afternoon, because it's noon already. Bayesian methods for radiometric calibration and motion picture encoding workflows. A translation to that might be probabilities to calculate how a camera encodes an image so that we can do conversions between color spaces easier, right? That might be another way to express it, but it was too long to fit in on the slide. A little bit of terminology clarification, because I actually make this, not mistake, but I tend to actually refer to this camera characteristic in different ways. And all of these terms kind of like mean the same thing. And when we talk about a camera response function, a radiometric response function, an opto-electronic camera function, or an opto-electronic transfer function, they're all referring to the way that the camera actually translates from linear light in the scene to a number that is stored in memory. And then we also have the term gamma, which is really is very related to it, but there's a slight difference to it that we'll get into it in a minute. So I stole this from Kodak from, I think it's about 25 years old or something like, or 20 years old, almost 20 years old, 2001, right? Just to give an idea of like, motion picture workflows and especially all the different inputs that can go into a post-production workflow, because that's kind of like one of the motivations that drives this project, is to actually be able to make it easier in terms of inputting sources from different capture devices into a post-production workflow, especially for the purposes of tone and color manipulation. So here, we can see, from all the types of different films to different electronic cameras, and of course, I'm missing here, but you could have also like CGI or anything like that, computer-generated imagery. And when we think about excuse me. When we think about combining footage in post-production, these are some of the things that we need to think about, right? We need to think about what type of maybe compression format is the data in, what type of frame rate, resolution, aspect ratios, all of those things have to be dealt with in post-production. And one of the most important ones is, of course, to understand how that device encoded the light from the scene for subsequent color space conversions or even color correction. And color correction actually is divided basically into two steps, right? One of them is what we call primary color correction and secondary color correction. Secondary color correction is where all the creative decisions are made and you make changes to the scene that fit the story. Primary color correction is basically, okay, how can we get all this footage together in a uniform way? All right, that it all looks kind of uniform to start with. So that's our part of our kind of like motivation. So thinking about what the camera does, this is a slide that basically summarizes that, right? In terms, and I'm sure I'm missing maybe one thing or two, but in general, the camera goes through all these processes when it actually detects, from the moment that it's detecting light until the moment that that light is stored in some type of memory. So, the sensor has to read, detect the light, pixel correction, corrections for vignetting effects, do white balancing, demosaicing, all of that. And, of course, part of it then is to actually be able to encode that linear light coming from the scene into a digital number, right? So, and then of course that we have any subsampling, unsampling, compression, save to storage, send to a display. So here is what we're going to worry about, right? It's like that OECF or OETF, camera response function. And so where does that function come from? Why do we have actually a function that we apply to be able to translate linear light into a code value? And there are a couple of reasons. One of them is kind of historical, and then it happened to match pretty well with our human visual system, and that's the reason why we still do it today, right? Old CRT monitors, or CRT monitors, not necessarily old, but CRT monitors, the relationship between drive voltage and the amount of luminance coming out of the screen for how the phosphors would behave is a nonlinear relationship. And the signal from a camera had to be pre-corrected to account for that. But at the same time, what happens is that if we account for that and pre-correct for that, we are encoding in a manner that mimics how our human visual system perceives lightness. And it is a very efficient way of encoding linear light. And that's the main reason why we still do that, why we still actually employ some type of nonlinear relationship between the linear light coming from the scene and the actual pixel value that is stored in a camera. As it says here, right, encoding video drive voltages places us in a very convenient perceptual space. And the gamma-corrected perceptual space today, the main benefit is that it allows us to use the limited, a limited number of bits or code values that we have available. We actually use them in a more efficient manner when we're actually encoding the light. Also, there are a couple of other effects that we take into account when we're actually encoding these code values and getting them ready for a display, all right? And I'm running through what some of the standards are, and then some of the non-standard ways of doing this. So we know that our human visual system, there's several phenomena that we experience when we're actually viewing images in different environments. If it's a bright lit room or if it's a dark room, there's going to be different effects that affect how we perceive the contrast of an image, for example. And to combat these effects, there are things that we do when we encode the signal, things like rendering intent, which is to compensate a little bit for that loss of contrast that might happen because we're looking at images in a darkened room. Okay, so, very well-known standard, Rec 709 for video, right? Excuse me, we're showing here kind of like what that function looks like, right? Relating luminance to a code value signal, a relative code value signal, and we can see that it has a nonlinear form. And without getting too much into the details right now, but when we actually pair this up with either traditional sRGB displays for video or the more popular now 1886 that assumes a 2.4 gamma for the display, we get a rendering intent contrast at the end of 1.1, 1.2, which is kind of like appropriate for viewing images under those environments. The key thing to take from here is that, okay, this is one standardized form of this encoding function that we use in a camera. Anytime you use your phone with recording video, it's encoding light utilizing this nonlinear function between the light from the scene and the code values that are stored. We also have kind of like the new standards coming into play, right, for dealing with high dynamic range, like hybrid log gamma and the Dolby PQ. Right? Now these also bring some other standards and some other ways of encoding this light. In some cases, PQ, right, is very centric in the decoding, and it has certain kind of like recommendations for how the camera should encode then the values that are going to end up going to a Dolby display, for example. And in the case of hybrid log gamma, also there are some other requirements, and the standard mimics somewhat the video standard with expanded range. But these are kind of like standard ways of doing this that are relatively well known when we actually design a camera or try to understand what a camera is doing. But we also have some that are not so standard, right? And it's the beauty of how our imaging industry works is that we have all these other manufacturers that, depending on their, the purpose of that camera, how it's going to be used, will have several different ways of encoding that linear light into a code value. Always kind of like taking into account some type of non-linearity that follows this benefit of encoding in a similar way as our human visual system. But what happens is that this brings a lot of headaches too in terms of post-production, in terms of being able to efficiently bring all of these different types of footage together, right? A little bit of history as to how this has been done in the past is the famous Cineon system that Kodak recommended and put in place many years ago in terms of how to best understand how film behaved and bring it into a digital pipeline, right? And many assumptions would be made at that time for good reasons, some of them not so good reasons. But for example, without getting too much into detail, but this is the way that you would convert, for example, a code value from a scanned film into a video value ready to be broadcasted before color correction or something like that. And this little thing that I'm pointing out here is the assumption that all film have a kind of like transfer function that is completely linear and that the slope is 0.6. Most of us know that no, film has nothing that is linear, right? That's part of the beauty of it, is how it treats the highlights and how it treats the shadows. Okay, so this was, now for good reasons, you need to have some kind of standard and some kind of way of doing this, repeatedly, but this would cause some errors in terms if we want to predict the exposure that film received so that we can do color correction and color space conversions appropriately, this would be a problem. And this is kind of like a similar problem to what happens today in many of these conversions. One of the latest, of course, systems that try to tackle this on and how to bring in content from different sources into a central common space is the Academy Color Encoding System, ACES. And as we know, it's a colorimetric appearance-defined color space, and also a high-precision system for encoding, mastering, and interchange of different sources. So thinking about this, right, and about the system, the ACES, down here we have, for example, an original scene either coming from a film camera, an original scene coming from a digital camera, and then what ACES calls the reference capture device, which is, in theory, if everybody had this camera, we wouldn't have, every output of that camera would be in ACES already. Well, the truth is that that camera doesn't exist, right? There's just many different models of cameras. So there's this step right here called the input device transform, which is a transform, a conversion, a matrix that is used to convert any real camera exposure value into ACES color encoding space. So this is very good, right? Because if we can actually, this is one example of like, we have this centralized encoding space that then would make it easier in terms of being able to manipulate and bring in all different kinds of content. So what we have here, though, is that this is just kind of like a little diagram showing what that, where that input device transform sits from the original scene and what the camera is capturing, all the way to then saying that these are ACES values. So right here, what we have is that this transform is really a 3x3 transform. And a 3x3 transform is really a linear transformation, right? So to be able to do this properly, what ACES recommends is that when we create an IDT, an input device transform, you need to be dealing with camera exposures that have been linearized, which means in a nutshell, that we need to understand what that nonlinear function was that the camera implemented to translate from scene to code value. So to be able to do this in a research environment or a university environment is fairly simple, right? For us to understand kind of like how camera behaves, do some measurements, and come up with what is actually this transform. The other part of the story, though, is that this is not only important for creating that transform, but when that transform is used in the industry in post-production, it's expecting that the data that is going to transform has already been linearized. So it also puts it's important that in post-production we also understand what this is. And then, so in ACES, that transform here, and if you look at the documentation for ACES, you'll find that this is basically kind of like how that matrix is created. And that matrix has two objectives, right? It's to convert camera exposures to that ACES reference input device. So it's basically saying, I want this camera to behave as that reference camera that ACES has specified. And to do that is trying to basically say, I want the exposures of this camera to be exactly or as close as possible to the exposures of that reference device. The only way that you can do that is if, with zero error or very minimum error, is if those two sets of spectral sensitivities for those cameras are actually linear combinations of each other. If they're not, you're always going to incur in a little bit of error or some error. Well, the second, let me back up here. And the second objective is that matrix is one matrix, but it actually also does chromatic adaptation because of ACES being a scene-referred appearance-encoded color space with a specific white point and things like that. But we're not going to get into that right now. But that's the purpose of that matrix is twofold. But the thing to remember is that it's important then to realize that the only way that this matrix corrects perfectly is if those two spectral sensitivities are linear combinations of each other, in which case that doesn't happen. And if you don't take into account the non-linearity that most cameras impart in encoding a signal, that's only going to make it worse. Like when you actually try to either come up with that input device transform or apply that input device transform. And this is just a little table showing, like, if I started from a linear signal that I know my images are linear, and I start deviating from that and kind of like applying like, some gamma deviation, then my error in the calculation of that matrix increases, right? As well as kind of like the error of trying to match, again, those original exposures. So all of these slides have been basically to kind of like lay out the motivation why we are interested in being able to calculate this or understand what this function is. So the radiometric calibration is the term used to actually understand this function for different capture devices. And one way to do it, like I was saying a couple minutes ago, is like if you have a nice lab or time in the university like we do, right? The easiest way to do this is to actually, select some charts that have a range of exposures that what that the luminance is that shines out of each of these patches, and you measure, right? You go and take a picture, and then what that relationship is going to be between, in this case, I have normalized exposure here and the code values here. Boom, very easy to do in a research environment. This actually, to be able to do this every single time in post-production, not so easy or not so practical, right? Where in post-production, you're getting constantly footage from this and that, or capture on this camera, or capture on that camera. And again, for some of that footage, you can assume that is a standard transfer function, right? Like we were talking about Rec 709 or some of the HDR transfer functions. For some other footage, you can't, right? If it comes from an ARRI shot, in one of its log modes, or a Sony camera shot on one of its log modes and things like that. Well, how can we try to at least maybe understand that or estimate that function only from pixel data, right? Without having any other information. Let's say you don't have any metadata and what, you just got footage. Or maybe you have some archival footage that came from some place that you don't know and you want to include it in whatever production you're working. It would be advantageous if we can understand this relationship so that we can do color space transformations appropriately. So some of the work that has been done, and these are referenced in the paper. Whoops, sorry. Trigger happy. Some of the work that has been done, right? So of course, direct measurements. All the other ones that I kind of like highlighting here, they are various methods that sometimes, most of the time, they require some additional constraint in the capture process. Meaning like, oh, I have to take the scene, but I got to take it at different exposures. Or I have to take the scene and also have a measurement of like the 3D space to know where the light was coming from, or things like that. So all of them are very, very kind of like smart ways of doing this and trying to infer the radiometric curve, but very non-practical when it comes to being able to do this only from pixel data. Except for one of them, which was kind of like the motivation where we started our work, which is single image calibration through color edge distributions. In this case, this paper looked at looking at any image and looking at edges between two colors, where you have one color falling on one side, one color falling on the other, and mixtures of those colors. We can start to actually use that information to try to infer what the non-linearity was that was applied in that camera. So before that, it's important for us, like if we're going to try to estimate this function, well, what kind of model do we use, right? It's like, an example would be, well, I'm going to assume that all cameras use a power function, that all cameras encode a signal using a power function. Well, might not be completely true. Some of them will use some log. If we saw from the Rec 709, actually that's not only a power function, it has a linear function at the beginning, right? So there's all these nuances that are important to understand. Well, back in 2002, 2003, I'm sorry, Grossberg and Nayar actually did an analysis of what were the most common kind of like radiometric response functions of the time. And they came up with a principal component decomposition of this. Basically what this is like, well, we can model any of this with an average response, which is this one, plus a linear combination of some basis functions in different amounts. So you give me, kind of like in this case, we used 5 different basis functions. So it's like, you give me these 5 parameters, and I can model pretty much any function in this space, right? Well, and that's kind of like where we start. We start by using this model as the model that we're going to implement when we try to infer this camera response function. So this paper, this is based on their paper, right? What they did was actually, here is this drawing here, or this diagram here from their paper actually shows that how they approach this, right? It's like, well, you know what? We know that if the image has been encoded linearly, there's no transfer function. It's just linear, a really linear relationship between the code value of that image and the light coming from the scene. If I look in 3-dimensional space across an edge, all these pixels, if I look across an edge here from this region to this region and I plot them, they're going to fall in a line, in a straight line. But as soon as I apply some kind of nonlinear function, there's going to be a nonlinear distribution in that 3D space. And they were like, wow, we can use this. We can use this as this feature that tells us what is, if a nonlinear function has been applied. So they actually use a Bayesian approach, which I'm going to describe in a minute, in which they create this distance function just to basically figure out how far this, for example, MP point is from the linear part where it should be. And they use that as a part of a probability to then come up with a best guess of what the parameters for this model should be that come out with the opposite or the inverse camera response function to actually correct for that nonlinearity. So they're basically saying, okay, give me data, let me look at this, let me try this inverse, and let me try this other inverse, or let me try this other inverse. And when this distance is minimized, it's like, okay, I've actually linearized these sets of values across pixel edges, and now I know what that response function should be. I know the inverse of it. Well, this is known as a MAP, as a Maximum A Posteriori approach in probabilities. And what that means is that you come up with one possible set of parameters for that model, right? Which is pretty good. This is how we mostly approach any problem where we're trying to infer or deduce some type of function. And here's where kind of like the Bayesian approach comes in. And the idea is that we typically, right, that is right here. And let me go through this very quickly. It's like there's this progression that has happened over the years in terms of statistical analysis and statistical thinking when using, for machine learning, for example. So this first one, what this is like when we create just prior knowledge without having any data. And an example of that would be, I show you a dice, right? And what your prior knowledge tells you is like, oh yeah, let's say that is a fair, I think automatically that's a fair dice. If I throw it, I have the same chances of getting a 1, of getting a 6, right, without getting into any nuances, but that's your prior knowledge without any data. Well, then we move and we say, well, let's start considering actually data. Let me start throwing that dice to start actually now getting information about this system, right? And then you start throwing it and then you start going like, well, I'm always getting a 1 or a 2. I'm always getting a 1 or a 2, right? Now you start kind of like changing your prior knowledge of that, oh, this is a fair dice. Now it's like, well, this might not be a fair dice. Let me collect more data to actually come up with a complete description of how this system actually works. So this is where we come into then taking into account now what we call a full Bayesian approach, in which we focus on calculating what is a posterior probability. This is what is the probability of the parameters of my model based on the data that I have. And to be able to do that is a combination of what we call this prior knowledge, right? I can say, well, I believe that all of these have similar probability of happening. I can assume that, for example. But then, once I start collecting data, that now this likelihood is the probability of the data based on a set of parameters, I can start to change what my prior belief is. And I can do this in this statistical way. So this is kind of like what we've been doing. The problem is that, as you can imagine, anytime, if we remember, right, anytime we see an integral, typically that means it's like, ooh, this is not going to be easy to calculate, right? This is going to be a pain. So, and that's kind of like the problem, right? When many approaches is like to maximize the likelihood, anytime you see the term ML, maximum likelihood, is by just looking at this here, right? And they maximize that looking at one output, one possible, what is the value of my parameters that makes this the maximum possible? And that's the result. And that's okay sometimes. What we're interested in is like, no, I want to know what the distribution of my possible parameters is, so I can make a more educated guess than just pointing out I'm picking the maximum of this distribution. Maybe I want to just base my result on calculating an average of that, and that's what we've done. So to do that, like I was saying, this integral is a problem, and what we do is that we use a Monte Carlo sampling algorithm to do this, okay? So to approximate this integral and make it be kind of like tractable or easier to compute this posterior probability. In a nutshell, kind of like a Monte Carlo sampling algorithm is like if I gave you a square and a circle where the square sides are the tangents to the circle, and I said, you know, a way to calculate the area of that circle would be if you sprinkled a whole bunch of grains of rice in there, right? And you know how many total you have inside the square, and then you count how many are inside the circle, and you create a proportion between the two. Very easy to calculate the area of the square. Let's say the area of the circle was difficult, which is, you know, it's not, but let's say it was. Then you can create this proportionality between the number of grains of rice that you have inside the circle versus the ones inside the square. And that is the same approach. The problem here is that many times we don't know what this is. It's very tough to, especially in a 5-dimensional model that we have. It's very untractable. It would be like a 5-dimensional integral. So the way that we try to do is like, okay, do we have any knowledge about that database and those parameters? And let's do a sampling algorithm through it so that we can approximate that. So once we do that, we come up with an approximation of the distribution of the parameters, those 5 parameters. These would be an approximation. These are the approximations of those distributions, probability distributions. And as you can see, sometimes it's like, well, if I pick the maximum here, it's going to be one good result. But it might be better to actually take the average of this, since this is not really kind of like a Gaussian exactly distribution. It's somewhat bimodal. So by doing this, we can then estimate this camera response function, and we've shown that it has some improvement, or has improved, over approaches that only use like a maximum likelihood or a maximum a posteriori approaches that use one specific value. What we do is we estimate these distributions, and we compute the mean value, and with that we model this dashed black line here. The green one, and we also have here kind of like the measured actual values to compare it to, and we've shown that it performs better at estimating that than kind of like previous methods here. Now, of course, it's tough to talk about machine learning without talking about neural networks, and that's something that we're looking into right now too, as to how a neural network could help understand better or extract a feature of the image that would give us more information that we can use in this model. And we can also use this Bayesian approach to, like, for example, train a neural network, and what's more important, compare different network architectures. This allows us to come up with the best solution based on your different models without actually having to have extra data to test your system. It's by applying that probability methodology, we can actually come up with what the best model would be based on the data that you have available. Look at that, 0, just in time. Oh no, I was 6 seconds over, damn it, sorry. Thank you, and questions? There's a test that I'm gonna pass through in a little bit. Yes?
Yeah, nice talk. It seems like by relying on the edge, you might have contamination from chromatic aberration of the lens, or is the technique able to see through that?
So absolutely. Not only that, but also there might be some trouble that we found with compression, you know, and distortion of the edge. So that's something that we're looking into trying to, we've used kind of like using multiple frames and averaging them. That's, of course, assuming that there's not a lot of motion in each of them. And that has helped with reducing some of the error that might be introduced because of some of those artifacts. Yeah. Oh, thank you.
Thank you for watching. If you enjoyed this video, please tap the like button and also subscribe to our channel to receive notifications when we add new content. For more information about us, please visit SMPTE.org. We'll see you next time.